So before the break, we were talking about asynchronous and synchronous. So asynchronous, where you have no bounds on the message delay. Synchronous, where you do. So asynchronous is actually very hard, and in the strict case when there's actually no bounds, there are impossibility results for consensus. Whereas in the synchronous case, it's actually very easy to do consensus. But the internet is not built as a synchronous system. You don't have any inherent bounds in the internet. So one of the first things we have to understand is, how do we go on now? How do we go on? Because it's actually possible in practice. So how does it work? Well, actually, we have to be a little bit more precise on how the internet is built. So we're actually going to look at basically the architecture of the internet. The architecture of the internet is actually hierarchical. It's a hierarchical system. We have local area networks that are very close, that are connected by bridges that are farther apart, and so and then continue. So there's a hierarchy, and the farther you get, the farther the nodes get, the more pieces of the system they have to traverse, the more routers they have to traverse. So what this means is that the internet is mostly synchronous in practice. So this is kind of an empirical observation, but you can make it rigorous if you look at the hierarchy of the internet. So if you look at internet nodes, okay, let me just make a bunch of nodes. Here. Then there's the nodes, the routing. Let's say these three nodes are connected on local area network. But if you look farther away, you have another level of routers and bridges. And if you look even farther, there's another level. So here there's another level, for example. Okay? So if this node A wants to talk to B, it's completely local. Whereas if A wants to talk to C, it goes to the next level, because C maybe has its own local neighborhood, but the neighborhoods are separate. But if A wants to talk to D, then it has to, this second neighborhood is actually not big enough. It has to go to another neighborhood even bigger. So you see you have these kind of neighborhoods. So this is kind of the architecture, the hierarchical architecture. So why is it like this? Why is the internet like this? Because of the way it's evolved. So usually the way it works is that a small organization connects itself, and then maybe it connects itself to other things that are somewhat farther away, in a town, and then in a province, and in a country, and so on. So basically the evolution of the internet favors the local connectivity, and then these local connections are connected to other ones to get bigger and bigger and bigger. It's because the universe, because the world is hierarchical, okay? Because it's much easier to talk to people when they're close together. The farther away you get, the harder it gets. So the internet mirrors that. So that it has this hierarchical structure. So what that means is that when A and B talk to each other, within this particular local neighborhood, there's actually a bound. This might be a local area network, for example, or it might be multi-core architecture where A and B are on different cores, or it might be a Wi-Fi or something. Huh? But there is a bound here. But it's not guaranteed. The bound is respected most of the time. That means most of the time, A and B can talk to each other with the bound. But assuming now that there is a lot of congestion, if there's some problem, typically it's congestion. The way that the internet works is that a protocol like IP is allowed to drop packets if there's congestion. Okay? So if there's congestion here, then they will not be able to talk here. So they have to go through another router. Okay? So maybe this connection does not work. They have to go to the higher level. So it starts where you have a low, so the small bound. So this is A and B talking to each other. you might have a larger bound, but most of the time A and B can talk directly. But sometimes they have to go to a larger bound, and so on. And this actually goes up a certain number of levels. So most of the time, the bound will be respected. So how can we handle that? So the idea is that most of the time the bound is respected, and occasionally they're violated. Rarely, but it can happen. There's no guarantee. There's no guarantee that the bound will be respected. Okay? Well, the way to handle that is to notice that when you're running an algorithm, that there will be some highest level. There will be some highest level in which the algorithm is going to run. Even if A and B cannot talk to each other directly, they have to go through the higher level. Well, at that point they can talk and the bound is increased, but the algorithm will run at the higher level. So there is some higher level where there will be bounds. Maybe the bounds are higher than the lowest, but they will be existing. Okay? So how do we model it? So basically, we can formally define this property, and we will define what's called a partially synchronous system. So a partially synchronous system means that the system is basically asynchronous. It starts by being asynchronous, and after a certain amount of time, it becomes synchronous. So there are bounds. So there are bounds that eventually become known. Okay? Starts asynchronous, and eventually becomes synchronous. So that means when you start communicating, you don't know how long it's going to take. Okay? You measure the time. It takes so much time, 10 microseconds. This one takes 100 microseconds. Okay, this one takes milliseconds. So you're running the algorithm, and when you're running the algorithm, you can see what the bounds are. But maybe this low bound is actually not good enough because maybe we're going to go to the higher level. It's rare, but it could happen. Well, then we can take higher bounds. Okay? So there will be some bounds that will eventually hold. It's just that we don't know which ones. So some bounds will eventually hold, but we don't know which one in the beginning. So in a partially synchronous system, so the idea is that when you start running it, you don't know what the bounds are, but you know that eventually means after some finite time, there will be some bounds. But you don't know what they are, because they might be these, the small ones, they might be the medium ones, they might be the higher ones. You don't know how far up you're going to go in the hierarchy. Most of the time you'll be low, but sometimes you go higher. So you don't know in the beginning how far up you go. So you don't know immediately what the bounds are, but you will eventually know them. So a partially synchronous system is actually making this precise. It's a formally defined system saying that the system starts out by being asynchronous. So there's no upper bound, and eventually, after some finite time, there are upper bounds. Okay? That means when you start running the system, the algorithm is running as if it's asynchronous, but after a certain time, there will be bounds. And then you can run it kind of like asynchronous. The problem is you don't know when. This is actually very tricky. We don't know when, but you know it will happen eventually. So you see, the internet is kind of a subtle construction of it. And it's actually inherently like this. There's really no way to make it much better than this. You can try to make guaranteed bounds, but it makes the internet much more complex and expensive. See, this is a very low-cost structure, okay? The problem with synchronous, if you want to make the system synchronous, it's going to be very expensive. You can get more synchrony, you have to pay. Asynchronous systems tend to be low cost. Okay? So a partially synchronous system is a very interesting compromise. And the internet is actually doing this compromise. Okay? So this we're going to, of course, see in the course. Huh? So the system starts by being asynchronous and eventually becomes synchronous. So if you do that, it turns out you can solve consensus here. You cannot solve it asynchronous. You can solve it here. And we'll see how to do it. Basically, you can solve it if there's less than half of the nodes crash. You can solve it. Asynchronous, it's impossible. And for synchronous, it's n-1. You can solve it. Everybody crashes except for one. But in a partially synchronous, you can solve it just less than half. So if you have 10 nodes, then 4 nodes can crash and you can still run consensus. Okay? So consensus is solvable in a partially synchronous system. So this is actually a very interesting and subtle result. So it holds for the internet. So all practical distributed algorithms are actually going to be here. Okay? They're all going to be made for partially synchronous systems. All realistic distributed systems are going to be partially synchronous. So, like the internet, but also other kinds of systems. And if you have a majority of correct nodes, a majority, so that means greater than n over 2, correct? So less than n over 2 crashes, then you can solve consensus. That's a very interesting and a non-trivial result. Okay? This is a major result. The first algorithm that actually demonstrated this was in the 1990s. This is called Paxos algorithm. And you have one guess as to the person who discovered this algorithm. LSINF2345, okay? So this was a major discovery, that you can actually have a partially synchronous consensus algorithm that works up to just less than n over 2 crashes, and it still works, okay? So in the course, we're going to be trying to understand this. So in the real world, distributed systems are going to be partially synchronous. They will not be asynchronous, not most general, and synchronous. Sometimes you can get synchronous systems, but it's actually very hard and very expensive to make synchronous systems. So if you have one, you're in luck, because life is easy. But in the real world, you will almost never have a synchronous system. Most of the time, you'll have a partially synchronous system. Okay? So that's kind of intuition. And I know that probably some of this is very obscure, but in the rest of the course, we're going to understand how all of this works. Okay? We're going to get into it slowly. We're going to understand why it's like this, why this is so important, and we're going to see practical algorithms here. So realistic internet algorithms are going to be partially synchronous. Okay? Useful for internet. Okay. Let me talk a little bit about failure now. So we talked about concurrency and synchrony, the partial synchronous. Let's talk about failures a little bit. So we'll give you some intuition. So nodes can crash. Okay. So we want to write algorithms that work when nodes crash. So how do we write those algorithms? Well, one of the very interesting ideas is called a failure detector. Basically, we have a black box that tells us when nodes are crashing. So that means the algorithm is simple. We're going to have a failure detector which encapsulates all of this sophisticated detection of whether the node has crashes. So, for example, it could be using heartbeats, where a node will send a message to another node and wait for a reply. It's like your heart beating, huh? And when there's no reply, then it knows that the other node has crashed. If the system is synchronous. If the system is asynchronous, it doesn't know anything. if the system is partially synchronous, it might start out by making mistakes, but after a while, it will make no more mistakes. So that's a very interesting property, actually. The failure detector sends a message, gets no reply. It thinks maybe the node crashed, but actually the reply comes, but it's slow. Okay, send a message, but now I know that the time bound has increased. Okay, because the message comes back slower. So I'm getting the heartbeats. I think the node is still not crashed. And then the message does not come back. I think the node crashed then. But maybe again it's slow, so I increase the bound. So the failure detector can start out by making mistakes. It thinks that the node crashed, but it did not really crash. But after some time, in a partially synchronous system, the bounds exist. There will be bounds, and the failure detector will figure out what the bounds are. And after that time, it will make no more mistakes. So the whole point is that the failure detector starts by making mistakes, but it kind of gets smarter, and eventually it makes no more mistakes. So the algorithms have to use that. Okay, you can start by not knowing if the nodes crash, but eventually you know. Okay, so that's how we're going to write the algorithms. So we're going to use failure detectors to implement consensus and atomic broadcast in partially synchronous system. Okay, in the rest of the course. Okay, so about failure. Right now, up to now, I only talk about one kind of failure, which is crash stop failure, which is the node crashes and just stops. This is, of course, a very common kind of failure, but it's not the only kind of failure. Let me talk about two other kinds now in the introduction. Two other kinds of failure to show you the kinds of things that can happen. The second kind is called the Byzantine Fault, and the third kind is called a self-stabilizing system, or it's for an algorithm that can repair itself when any amount of temporary errors. So let me show you first. A Byzantine fault, it's more complicated than crashing. It's the node starts behaving arbitrarily. Maybe it's smart and there's like a security breach, and the node is trying to break the system. Okay? It's can arbitrarily, so it can be very smart. Maybe there's a security breach, maybe there's a hacker got into your system, and the node is trying to send messages exactly in the right way to break the rest of the system. That's the worst case, huh? So the node behaves arbitrarily, and it could be malicious, can be malicious. So a Byzantine algorithm is actually able to tolerate that. It works. There's also a famous algorithm by LSINF called the Byzantine Generals algorithm. Let's say you have a bunch of generals. Each one has their own army. There's 10 generals, okay? For example, 10 generals, but 2 of them are traitors. They're actually working for the enemy, and they're trying to make things go wrong. So when the 8 good generals are trying to agree on a time for the battle, the 2 other ones are trying to make it so the other ones, they don't agree, okay? They're trying to mess things up. So how can it work? Well, it turns out you can actually formalize this, make algorithm for this, and it works if the number of traitors is maximum 1/3. So typically, if you have 10 generals, if you have 3 traitors, you can still work. The 7 good ones can still do the right thing, because there's only a small number of traitors. And they don't know who the traitors are, of course, huh? The 7 good ones, there's 10, but you don't know which ones are the traitors. Huh? You only know that there's maximum 3. But if there will be 4 traitors out of 10, it's more than 1/3, then it doesn't work anymore. Then the 4 can actually mess things up. So the Byzantine algorithm So it's not n over 2 anymore for consensus, it's n over 3. Okay? You need more. You need 2/3 good guys to make it work. Okay? Where a non-Byzantine algorithm can often tolerate that half of them are faulty, like consensus, all you need is a majority, slightly more than half. Byzantine algorithm, you need more than that. It's logical, because the bad guys in a Byzantine algorithm, they can be malicious. They are actively trying to break the system. Okay? So Byzantine algorithm is a big area in distributed systems when you're very critical applications based on that are working in these high top security environments. Okay? So Byzantine algorithms, when you can expect some of the nodes to be traitors, you will use algorithms like this. So an algorithm like the Bitcoin blockchain algorithm is a form of Byzantine algorithm. Okay? It's able to do consensus even if you have malicious nodes in the system. Okay? So we're not going to talk so much about Byzantine algorithm in the course, but this is just to tell you that this is like an extreme case of algorithms that work when even you have very, very nasty nodes. Okay? So that's Byzantine. So that's kind of an extreme case. Byzantine crash. Self-stabilizing is another case. So a self-stabilizing system is another extreme case. So Byzantine algorithm, you basically have malicious nodes, a small number of malicious nodes, of bad guys. In a self-stabilizing algorithm, everybody can go bad, but only for a short time. All nodes can go bad, but only temporarily. So the difference is that a Byzantine algorithm, a small number of guys are bad forever, permanently bad, whereas in self-stabilizing, all of them can go bad, but only for temporary, and after that time they're good again. So it's like you shake the state of the system. Cosmic rays are hitting the system, and all the nodes go crazy, okay? Like in space. And self-stabilizing algorithm, once the cosmic rays go away, it will repair itself. That's pretty amazing, actually. They all go crazy for a short time, but only temporarily. And once they get back to normal again, then it repairs itself. So human beings are kind of like this, huh? If you go to a party and everybody gets very drunk, then nothing happens again. Society doesn't work. All these drunkards, they don't do anything. But the next day, they all wake up, they're back to normal, and everything goes back to normal. Okay, so that's kind of like self-stabilizing algorithm, where everybody goes bad, but only temporarily. Whereas Byzantine is where you have like traitors that are permanently bad, but only in a small number. And the Byzantine algorithm can handle a small number of traitors. So you can see the two extremes, huh? A small number of permanently bad guys, or here, a large number of temporarily bad guys. Okay? So the system might temporarily be incorrect, but eventually it becomes correct. So we can make this more precise. The system can either be in a legitimate state or an illegitimate state. So legitimate state means that things are going well, whereas illegitimate state means the system is kind of crazy. Okay? So when we design our algorithm, we have to define two properties. So if the system is in an illegitimate state, yes?
Does the system know that it is in
no, it doesn't know.
Okay.
It doesn't know. There's no way. It doesn't know. It's just the algorithm is designed that if someone from the outside looks at the system, you can see it's in an illegitimate state. But the system itself does not know that. It also does not know whether the nodes are traitors or anything in Byzantine. So there's a lack of knowledge. So when you define the algorithm, you have to have these two properties. So if it's crazy, if the nodes are crazy, illegitimate, then they will eventually, if you execute the algorithm, you will go to a legitimate state. And closure means if you're in a legitimate state, you will stay in a legitimate state. So you need these two properties when you define the algorithm: convergence and closure. But let me give you a simple example of such an algorithm. So, okay, the advantage, of course, of self-stabilizing is that in any kind of a transient failure, it will be robust. You don't even need to initialize the system. You just turn it on, and it's in some random state. Fine, it'll repair itself. You can also compose them. If I have two blocks that are self-stabilizing, if the first one is going crazy, it sends crazy information to the second one. It's okay, because the first one will eventually repair itself. Then it starts sending good information to the second one, and then from that point on, the second one will also start to repair itself. So that means the system really is very robust to transient failures. So here's a typical example. So this example actually was used in early networking systems. It's called a token ring algorithm. So in an early network, so this was about the same time Ethernet was invented, there was a token ring algorithm. So each of these nodes is a computing node. Each node is connected to a successor and a predecessor. So their nodes are connected as a ring. So the way that the algorithm works is that there's a token, which I make my little box here. A token, which is a special value, which is basically propagated around the ring. It circulates around the ring. And the way to send messages on this network is that you wait until the token arrives, you attach your message to the token and you send it on. And then when the token arrives at the destination, the message is dropped. So this will guarantee that there's no conflicts, no congestion, no confusion. This algorithm will run at guaranteed speeds. So it's like a synchronous system. It actually makes messages very, very synchronous. But if there's an error, what if there's some kind of a bug? Maybe there's 2 tokens in the system, or 0 tokens. It's like broken, there's no tokens. Well, actually, it's possible to define an algorithm with a simple piece of code at each node such that their system will repair itself. There will always be exactly 1 token. So if there's 2 tokens, for example, then 1 token will always disappear. If there's 0 tokens, then eventually a token will reappear in the system. Okay? Actually, the code is actually not that complicated. This algorithm was originally invented by Dijkstra. You've heard of him. So this is not Lamport. He didn't do everything. So, who invented this algorithm, and it was basically the very first self-stabilizing algorithm, that you can actually build a system that repairs itself from all kinds of temporary errors. Okay, so one of the most used for these algorithms is a token ring algorithm. So these are 2 kinds of extreme cases. Most of the time in this course, we're going to stick to crash stop, or maybe some variations. These are by far the most frequent. Crash stop is a very frequent case, but it's interesting to know the extreme cases. And then in the rest of the course, so we're going to present you partially synchronous systems, algorithms that work there, and with different failure models, okay? And then, in the second half of the course, we're going to talk about large-scale systems, very large systems when you have thousands, or hundreds of thousands, or millions of nodes. We're going to talk also about dynamic systems, when you have new nodes coming in, or nodes leaving the system, like groups, rapidly changing number of nodes, and even where you don't really know how many nodes are in the system. If I have groups, like a large chat or Facebook pages, where you really don't know how many nodes are in the group. So very large systems tend to be dynamic, okay? Small systems tend to be static. So during the second half of the course, we're going to be talking more about large distributed systems. So typical examples that are used in practice: Skype, BitTorrent, PP Live, peer-to-peer algorithms, gossip algorithms, and we'll also talk about algorithms used in cloud computing, edge computing, Internet of Things, like the project. So basically the course, to summarize that, the course is going to be organized as follows. In the first half of the course, we're going to be looking at basically small, mostly static systems. This is already hard enough, huh? Using partially synchronous model. And in the second half of the course, we're going to talk about large systems. But a large distributed system will almost always be dynamic. It's very hard for a large system to be static. If I have a system of 100,000 nodes, it's very hard to keep it exactly 100,000. Huh? So large systems will almost always be dynamic systems. So we're going to look at some typical techniques for this. So typical techniques are either peer-to-peer or gossip algorithms. So you need both. Huh? For example, in banks, if I have distributed databases, I will usually have a small number of copies. I have maybe, let's say I have 5 copies of the database, Société Générale or Paribas, whatever, they have maybe 5. I don't know how many, they maybe don't tell, but it's something like that, because the databases are huge. So they have a small number, and the number does not change, usually. But things can happen. Maybe one of the buildings burns down, maybe the internet connection goes down, so there can be failure, okay, here. So this is what we will see in the first half of the course. The second half is a case which you see often in social networks. We have a very large system. I have a large group. For example, Twitter, where you can have millions of followers. A person can have millions of followers. Well, this makes a very large group. And that number can change all the time. Okay? So the large system will always be dynamic, almost by definition. It's very hard to be large and static, okay? So, and there are algorithms for doing this that are very different from the small algorithms because of this dynamic nature. So we're going to talk about peer-to-peer gossip. So basically, these are 2 complementary parts of the area of distributed algorithms. Both of those are very important. So we're going to start with the small-scale systems, and this will give you the really good intuition about partial synchrony. So this is how the internet is built. Huh? It's a partially synchronous system. It's very important to understand how this system works. So we're going to start here, and in the second half we're going to broaden our view and look at large systems. Okay? So that's basically how we're going to continue working. So basically, just to summarize this whole today's lecture. So today, I basically gave you kind of a view of the whole course, tried to point you to some of the really important ideas and why it's not so simple, and why partial synchrony is an interesting idea, but why it's actually complicated, why asynchrony is actually the simplest kind of distributed system, very hard or impossible. Also the core problems, such as consensus, broadcast. There's variations I didn't talk about, like leader election. Leader election is a kind of simplified version of consensus, where all the nodes have to agree on one node, which is the leader, like the president or whatever, the king, who is the leader of the nodes. So they have to run some algorithm, and it's simpler than consensus because the result is not just not an arbitrary value. It's actually the identity of one of the nodes. One of the nodes is like the president, okay, or the boss. So this is an important algorithm. There's also algorithms based on causality, where you have causal connection. If I have a chat group, for example, if I send a message to my friend sends a message to a third guy, then someone who's listening to the conversation has to receive the messages in the same order, okay? Because there's a causal connection. So that requires some work. Okay? That's also a core problem. Don't mention it here, but the causality. And then failure. So failure is normal. Failure scenarios. What do you do? Well, you have to keep working. So failure is both good and bad. It's good because it increases reliability. The bank can keep on running even if one of the databases crashes. But it's bad because the algorithm is more complex. Okay? You have to do work to get that. So different kinds of failure scenarios. So a simple one is crash stop. Most of the time we'll talk about this one. Two extreme cases are Byzantine and self-stabilizing. Now, Byzantine, where you have a small number of permanent bad guys. Self-stabilizing, where everybody can go bad, but only a short time. And then we're going to finish up the second half of the course by looking at large dynamic systems, which is more and more important today. So this is actually, there could be actually a whole course based just on this. And next year there will be a course called Large-Scale Structures on the Internet. So this will actually turn into a whole course.